In this notebook, you'll build a DCGAN and train it to generate new kinds of images. Specifically, we'll be building off of what we already know from generating MNIST images and address a more complex task. We'll be training a DCGAN on the Street View House Numbers, or SVHN, dataset. These are color images of house numbers collected from Google Street View. SVHN images are in color and much more variable than MNIST images. And our goal here will be to create a DCGAN that can generate new, realistic-looking images of house numbers. We'll go through a series of steps to do this. First, we'll load in and pre-process the dataset. Then, your big task will be to define and train discriminator and generator networks. After training for some number of epochs, we'll look at some stats, visualize the loss over time, and look at some sample-generated images. Now, since this dataset is more complex than our MNIST data, we'll need a deeper network to actually identify patterns in these images and be able to generate new ones. Specifically, we'll use a series of convolutional or transposed convolutional layers in the discriminator and generator. It's also necessary to use batch normalization to get these convolutional networks to train. Besides these changes in network structure, training the discriminator and generator networks should be the same as before. That is, the discriminator will alternate training on real and fake generated images, and the generator will aim to trick the discriminator into thinking that its generated images are as real or as realistic as possible. So let's start by loading in our usual resources, and then loading in the data. The SVHN training data is a dataset that's built into the PyTorch datasets library, and here I'm loading that in and applying a tensor transformation. So all the images are loaded in as tensor image types. Then I'm using a data loader to batch this data into a batch size I specify, in this case 128. This is the number of images we'll iterate over in a batch during training. You can also see that I've set shuffle to true, and this creates a final train loader. Alright, so after I've loaded in my data, in this cell I'm actually going to visualize that data, just to make sure it's as I expect. So here I'm plotting 20 of these images, and each of these is a 32 by 32 image with 3 color channels, RGB. These are the real training images that will pass to the discriminator. Notice that each image has only one associated numerical label. This is true even if the image contains multiple numbers. The labels look at the number that is clearest and in the center of the image. Now, your first task will be to do a little bit of pre-processing. We know that the output of a TAN-H activated generator will contain pixel values in a range from -1 to 1. And so, we need to rescale our training images to this same range from -1 to 1. Right now, they're in a range from 0 to 1, and I'm going to print out the low and high pixel values for an example image here. You can see that the minimum value is about 0, and the maximum is 0.7 for an example image. Next, I want you to complete this scale function, such that it takes in a training image x and a feature range -1 to 1, and it scales x so that its pixel values are in that range. So it should return a scaled x. Then, I've provided some testing code for you here that applies our scale function to our test image. And if you've implemented this correctly, you should see that the minimum pixel value is a negative value. As usual, if you get stuck or want to check your work, you can look at my solution next.